referring to them as an ester. When we get into the next chapter, which will also be on video, we're going to look carefully at the chemistry of carboxylic acid derivatives, including esters, so you'll see them again shortly. What we need to do now is to not only appreciate the overall reaction, that's what I showed you here, the overall reaction called a Fischer esterification, but we need to appreciate the mechanism of this reaction. So we're going to work through the mechanism right now. The mechanism of a Fischer esterification. Before I give you the mechanism, I'm going to give you a specific reaction. So I won't use R groups, I'll use specific things. So let's go back to benzoic acid. And we're going to allow that to react with ethanol under acidic conditions. And that is going to produce the corresponding ethyl ester of benzoic acid. We would call it an ethyl benzoate. We'll talk more about nomenclature of esters in the next chapter. But there it is, the ethanol right here. I'm circling a piece of the ethanol, everything except the hydrogen. There it is right there on the ester. Plus, notice I didn't circle that hydrogen, and I didn't show this OH group. That's gone too. Well, the H and the OH combine to form H2O. That's the byproduct. So this is the overall reaction that we're going to look at, and we're going to go through the mechanism. This is going to be another one of those mechanisms which is kind of long. It's got a lot of acid-base steps in it, but they're kind of all very closely related to one another, or at least there's a lot of steps that look very similar to one another. Well, I've got a carbonyl-containing molecule, happens to be a carboxylic acid, and I'm using an acid catalyst. As I've told you in the past, each and every time you see a carbonyl-containing compound, whether it's an aldehyde, a ketone, a carboxylic acid, an ester, anything, under acidic conditions, the first step of the mechanism will always be the same, and that is protonation of the carbonyl oxygen. Once you protonate the carbonyl oxygen, you produce a superelectrophile. The carbonyl carbon is already electrophilic, but once it's protonated at oxygen, it becomes a superelectrophile because this resonance form, which I'm drawing right here, turns out to be pretty significant. And in this resonance form, you see that there's a formal positive charge at that carbonyl carbon. So the first step is protonation. Think about what you're trying to do. You're trying to put this ethanol group on. So you're going to have to bring in the ethanol at some point, and that some point is right now. Bring it in. Ethanol is not a very strong nucleophile, but I've got a superelectrophile here, and so it's going to add on pretty quickly and pretty efficiently. And when you bring in ethanol, the first thing you form is this oxonium ion. Now, what we're going to do is we're just going to bring another equivalent of ethanol along to pick up that acidic proton in order to give us an intermediate, which is most definitely not a very happy one. It's not a very happy one because this carbon is attached to 3 oxygens. That's a pretty unusual situation in organic chemistry. There aren't a lot of examples like that. Normally, carbon doesn't like to be attached to 3 heteroatoms. The one exception would be halogens. It doesn't mind being attached to 3 halogens, although that's a fairly reactive species. But 3 oxygens at the same time, not generally very good. I just picked up the acidic proton with that alcohol, so now that alcohol is present as the oxonium ion. It's now the acid-carrying species in solution. Here's where we are. You always have to go back and look at where you're trying to go. We've got the ethanol molecule added in, but we've got too many bonds to oxygen here compared to where we want to be in our final product. We want to have a carbonyl group back. We've got to get rid of one of these oxygens very clearly. And the way we're going to do it is we're going to take one of them. I'm just going to arbitrarily choose the one on the bottom here, and we're going to allow it to be protonated using our acidic species. So I'm just doing a series of acid-based steps. I protonated the carboxylic acid, then I brought in ethanol, then I deprotonated, now I'm reprotonating at one of those hydroxyl groups. And when I reprotonate, look what happens. Now I've got an oxonium ion here, OH2+. That's water, that's a good leaving group, and we are going to allow it to leave. So there it goes. The reason I can allow it to leave is that the carbocation that will be left behind is going to be resonance delocalized. It's going to be a very good cation. There's the carbocation that is left behind. Let me make that a smaller equilibrium arrow. And here's the water that was spit out, liberated. In fact, that's going to be the water that is one of the byproducts. So I just made one of the products already, water. Unfortunately, it's not the interesting product. But I'm actually very close to making my ester. In fact, I talked about this being a resonance delocalized carbocation. Look at the other resonance form. Take one of those lone pairs on that hydroxyl group, bring it down to form a pi bond, and look at the corresponding resonance form. It is, in fact, my ester. It's just a protonated ester. All I have to do is bring in one more equivalent of ethanol. Remember, ethanol is the thing I've got a large excess of. Presumably, I'm trying to drive this towards ester right here, so I'm adding a lot of ethanol, a lot of alcohol, which happens to be ethanol in this example, and there it is. I now have produced my final product, plus I have regenerated my acid catalyst. In that last step, I regenerate the acid catalyst. The truth of the matter is, if you go through this mechanism, I use the acid and regenerate it several times. But what's key is that when you produce product, you regenerate it one last time so that it can then go on and start to react with more carboxylic acid and start the process all over again. That is the Fischer esterification. I probably should have put that title up at the top so that when you go back and look at your notes, you understand that that's what the reaction mechanism is that we've just gone over. The overall reaction on top, the mechanism down below. The Fischer esterification. Once again, I know I've said it before, but I want to emphasize one last time that in the left to right direction, carboxylic acid plus alcohol giving ester plus water, in the left to right direction, water is formed. You can drive this thing to completion if you get rid of the water, or if you just use a large amount of alcohol. That will drive the thing to completion. It is also possible, however, to drive the equilibrium in the opposite direction. So if you had a large amount of ester, and you added water under acidic conditions, you would make the corresponding acid. We'll come back to that idea in just a few minutes when we talk about soaps. Fischer esterification, what an important reaction it is. Well, these days, you've learned so many reactions. A really good way to see if you understand the chemistry you're learning is to apply it. And in my opinion, one of the best ways to apply these reactions is in synthesis problems. So, let's try it. See if you can start with propene and produce this ester. This is a methyl ester of butanoic acid. If it were the carboxylic acid, it would be a 4-carbon carboxylic acid, but it's the methyl ester of the carboxylic acid. We would refer to this as a methyl butanoate. How could we do this? This might be a good time to turn off the video and work on this problem and then turn it back on, and I'll show you how to do it. Okay, we're back on, and I'm going to show you how to do this. It's actually quite similar to the synthesis problem I gave you a few minutes ago, earlier in this lecture. So for example, if we begin with an anti-Markovnikov then you can take that 1-bromopropane and convert it into a organometallic. I think the last time, if I'm not mistaken, I converted it to an organolithium. So this time I'm going to switch it up and convert it into a Grignard reagent. And those would be the conditions to do it. Why do I want to do this? Because I want to get to a carboxylic acid, and I know that an organometallic can be reacted with dry ice, followed by a quench step, H2O, H3O+, and I will convert the 3-carbon organometallic into the 4-carbon carboxylic acid. I'm almost there. All I have to do is convert my carboxylic acid into a methyl ester, and the way I do that is to use a Fischer esterification. So I'm going to use a large excess of methanol. Why methanol? Well, because clearly I'm trying to make the methyl ester, and it must have derived from methanol. So I'm going to use excess methanol under acidic condition. And as long as I use excess methanol, I don't have to show this as reversible because I'm taking advantage of Le Chatelier's principle, and in a synthesis problem, that's a good thing to do because we're usually trying to make large quantities of whatever it is we're trying to make. So there it is. 1, 2, 3, 4 steps, 5 if you count the quench as a separate step. The synthesis of a carboxylic acid, followed by esterification, a Fischer esterification. Okay. Well, reactions of carboxylic acids, we've covered the tough one, the Fischer esterification, and now we get to cover a few fun examples. So for example, our next reaction is the reaction of carboxylic acids with diazomethane. The reaction with diazomethane. Now if you look carefully at what I've drawn there, I've got 2 resonance forms for diazomethane. Diazomethane is an unusual species for sure, but it's one that you've seen before. I don't know if you remember this, but all the way back in Organic Chemistry 1, we used diazomethane as a source of carbene in order to cyclopropionate an alkene. So let me refresh your memory. Recall that we can take an alkene, I'll just arbitrarily choose cyclohexene as my alkene, and treat it with diazomethane under photolytic conditions, meaning add light, and you will produce carbene, which can add across the double bond in order to form a new cyclopropane derivative. How does this happen? Well, it turns out that one of those resonance forms, the one that I showed you down here just a minute ago, looks like this. And that's a pretty important resonance form. Under these conditions, if you shine light on the diazomethane, you can break the carbon-nitrogen bond in order to form methylene, a highly reactive carbene species, plus nitrogen gas. And because nitrogen is a gas, it escapes. The reaction is not reversible, and the carbene simply adds across the pi bond. If you remember, the carbene has an empty p orbital as well as an sp2 orbital in which the lone pair is held. And so if you add this across the pi bond, what happens is the pi electrons attack the empty p orbital, the lone pair bites back down in order to form the cyclopropionation product. So that was where you've seen diazomethane in the past. Now we're going to look at a completely new reaction here, the reaction with a carboxylic acid, but we're still going to have to know and appreciate what the structure of diazomethane is, so I'm just going to go ahead and leave that on the board right there. This is actually a fun reaction. I like this one a lot. We're going to take a carboxylic acid. I'm going to give you the overall reaction right now. I'm going to start with benzoic acid, and we're going to treat that with diazomethane. In this particular case, in this esterification reaction, you do not need light. We're not going to form a carbene like we did in that cyclopropionation case. We're just going to allow the carboxylic acid to react straight away with diazomethane, and it will straight away, in a very clever way, produce an ester, and the ester will always be the methyl ester. So in some ways, this is a limiting reaction because we can only produce one ester, the methyl ester of whatever carboxylic acid we started with. The other byproduct will in fact turn out to be nitrogen gas, which once again escapes. How does this reaction actually work? Here's the mechanism, which I think is quite interesting. I'm going to go back to my carboxylic acid here. And what I want you to notice is that in this particular resonance form of diazomethane, this methylene group out here has got this negative charge. Diazomethane is a funny compound in which this particular resonance form with two formal charges is in fact a very good one for the structure. So I'm going to treat this carbon as though it were basic. It should be nucleophilic and it should be basic given its structure here. Well, in the presence of an acid like a carboxylic acid, I'm going to treat it as a base, which means I'm going to treat it as a Bronsted base. I'm going to let it come in and pick up an acidic proton from my carboxylic acid. And the aeroformalism for that would look just like this. The result is I'm going to form a carboxylate anion. There it is. There's my carboxylate anion, which results when I protonate diazomethane. And look at the diazomethane. It's now got a methyl group. It picked up a proton, which is attached to an N2+. Maybe I should spell that out the way I did the first time so you don't get confused. An N2+ group. Two things here. One, we haven't talked about it before, but the carboxylate anion, this conjugate base of the carboxylic acid, like most bases, can also be a nucleophile. That oxygen is somewhat nucleophilic. Now, I will tell you, it's not a great nucleophile. It's certainly not one of the world's greatest nucleophiles. It's not as strong a nucleophile as a simple alkoxide would be if I didn't have that carbonyl there. With that carbonyl there, the negative charge is delocalized between both oxygens. You can show another resonance form, which will indicate that. And that has the effect of reducing the amount of negative charge character that's on either of those oxygens. And so it's sort of spreading out the charge. It's that hot potato theory, stabilizing the anion by spreading out the charge. But because the charge is spread out, it's less nucleophilic. It's more stable, less reactive. If it were a simple alkoxide like that, it would be a much stronger nucleophile. But as a carboxylate anion, it's not nearly as strong. However, what we have inadvertently done, and actually I think quite interestingly done, by protonating diazomethane, we have created probably the greatest SN2 substrate there is in the world. First of all, it's a methyl substrate, and we know that methyl substrates are particularly good for SN2 reactions because they're not hindered at all. The methyl group is very small, and the nucleophile can get into that carbon atom very easily on the back of the leaving group. And this is a fantastic leaving group. Of all the leaving groups that we've looked at in our SN2 days, this is by far the best. This is a great leaving group. This diazocation is actually going to leave as nitrogen gas, as stable N2. And the result is, at the end of this SN2 step, which is the second step, you have prepared the corresponding methyl ester. There's the new bond as part of that SN2 reaction, plus your leaving group is neutral, stable nitrogen gas, which just goes away. No chance of this being reversible because the nitrogen escapes. So it's a simple one-pot synthesis. It does have two steps in it mechanistically. First, the acid protonates the diazomethane, and then there's this SN2 reaction that takes place very rapidly afterwards. But it's all done in one pot, one step from a preparation perspective, and you're done. So let's look at one or two examples of where we could use this. Here's a synthesis problem. If we start with benzene, we could chlorinate in standard way to produce chlorobenzene, which then could be converted into the corresponding organolithium, which in turn could be converted into the corresponding carboxylic acid via reaction with dry ice in the first step and H3O plus in the second step, and that carboxylic acid is in fact benzoic acid. From the benzoic acid stage, I actually have two paths. I could just react this with diazomethane to produce the corresponding methyl ester. Since it's a methyl ester I'm trying to make, it'll work just fine. If it were an ethyl or a propyl or an isopropyl ester or any other kind of ester, this reaction wouldn't work. Only diazomethane can be used to produce the methyl ester. But it should be pointed out that you could also do this through a Fischer esterification by using excess methanol under acidic conditions. You would produce the same product. So synthetically, you've got a couple of different ways to make methyl esters, and that's a good thing. They're important species. All right. We have done quite a bit here. We have performed a Fischer esterification, and we've made methyl esters from diazomethanes. There's only a couple more reactions I need to show you. One is the formation of amides using DCC, and the other is the formation of acid chlorides using thionyl chloride, and finally, the reaction of ketones using two equivalents of organolithium. And I'm going to show you those in just a moment.